6. Problem
Okay.
13.
Pull this thing over here. Chapter 6, number
13.
Okay.
So it's a fairly easy problem, but you get like a different answer based off whether you integrate with respect to y or x first. Because of like I guess the time intervals. So I was kind of wondering like,
Oh, wait, I'm looking at the wrong problem. Sorry.
uh,
I'm looking at the theoretical exercises. I was like, what? That one, 6.13, that would have to do with the gamma distribution, actually. Sorry. So let me see. A man and a woman agree to meet at a certain location about 12:30 p.m. If the man arrives at a time uniformly distributed between 12:15 and 12:45, and if the woman independently arrives at a time uniformly distributed between 12 and 1, find the probability that the first to arrive waits no longer than 5 minutes. Okay. All right, so how did you set that up, Matthew?
so I set x as a uniform variable over like an interval of 30, and then y is uniform over an interval of 60.
Okay.
And then the joint probability was 1 over 30 times 60, or 1800. And you have to integrate first with respect to y,
Okay.
because I think the intervals being different.
Right, so 30 times 60 is 1800, right? So the density is just going to be constantly 1 over 30 times 60. That's what you have, right?
Yes.
For 30 times 60 over the rectangle, uh, where x goes between 0 and 30, and y goes between 0 and 60, right? So that's kind of what you're looking at here. Okay. And you want the probability that the first to arrive waits no longer than 5 minutes. Oh, and by the way, I mean, it's worth noting that they mentioned 12:30. They said that that's a time they agreed to meet. It's obvious that that's like the average of each one of those time intervals, right? but one of them is clearly more flippant with their time than the other, but they're both fairly flippant. Okay, so how did you set up the integral for the probability in question?
So I did the integral from 15 to 45, and then the integral from x minus 5 to x plus 5, 1 over 1800 dy dx,
Yeah,
which works out to the correct answer.
yeah. So, okay, the first to arrive waits no longer than 5 minutes. Okay, so you integrated, so the outside variable for you was y, is that correct?
No, I used x as the outside variable.
Okay, so x was going, oh, right. So you have dy dx,
Yeah.
okay? So dx, so x is going between 0 and 30 apparently, or what?
I did 15 to 45 for x to just keep the time interval.
Oh, I see. So x was going between 15 and 45. Right. And then y, in order to be, wait's no longer than 5 minutes. And so you said the inner limits of integration were x minus 5 to x plus 5.
Yes.
But then, so what you're saying is whatever x is, y has to be in the interval from x minus 5 to x plus 5. That's what you're saying.
Yes.
Well, so if y arrives between x minus 5 and x, that means y didn't have to wait more than 5 minutes, right?
Yes.
And if y arrives between x and x plus 5, that means x didn't have to wait more than 5 minutes. Yes. All right, I believe that. Yeah. So that's the correct integral. But you're saying that if you integrate in the other direction, you get the wrong thing?
Yeah. I assume it's because x is limited to the time interval 15 minutes to 45-minute time interval. So
Well,
like if you try to
okay.
integrate from
So you have
0
to
to
figure
6.
out what okay, so the limits of integration are x goes between 15 and 45, right?
Yes.
So let's think about what that looks like. Oh man, I'm sorry. Well, actually, hang on. Can you just give me a second? I'm gonna go get my iPad. I forgot to bring that up here. Okay, can you just can you wait a minute? Hang on. So okay. So you're just doing 1 dy dx or something, right? So what
Yeah.
does that region of integration look like? What does that region of integration? Okay, so what does this region of integration look like? So let's sort of sort that out, all right? So I think it looks like this. Um, so there's like 15 and 45. This is not going to be to scale, okay? And then x minus 5 and x plus 5. Those two lines are going to be parallel. You understand?
Yeah.
So it's going to be something like this, and then something like this, right? So you're going to have like a parallelogram region like this. Does that make sense?
Yeah.
So when you go to integrate in the other direction, that's going to be kind of complicated. You know why? Right. So if I flip the order of integration, that's going to be fairly complicated because I'm going to like because okay, y is going to be the thing that's going to travel between numbers now. And first of all, you're going to have to figure out what values y travels between. But this number is going to be a critical one, but so is this one, and so is this one. I don't know if those end up being the same, but my picture is perhaps not to scale. But this one right here is going to be a different number. It seems to me that what x travels between depends, right? Depends on where y is. So like if y is up in this region right here, then x is traveling between the line and the number 45. Yes?
Yeah.
Whereas if y is in this region right here, well, then x is traveling between 15 and 45. Yeah? Whereas if y is in this region right here, then x is going to be traveling between 15 and this line. So what does that tell you you're going to have to do with this integral if you flip the limits of integration?
Split it up.
You're going to have to
Or-
split it up. Did you do that?
No.
Okay.
Okay.
That's got to be the problem. Right.
Okay.
But let's actually, I like doing stuff like this. Okay. So let's think about this. Okay. This is just good review. So 15 is less than or equal to x is less than or equal to 45, right? And x minus 5 is less than or equal to y is less than or equal to x plus 5. Okay. So first of all, what numbers is y going to go between? So we got to translate this into an integral where y goes between numbers. Okay. What numbers is y going to go between? Well, first of all, here, let's do this. So where is this? Okay, so where is this thing right here? Okay, so let's first find that intersection point. Okay, so where does that happen? Well, let's find all. Okay, first of all, we know what all of. Okay, we need to find all of these intersection points. Okay, and we need to find this, and we need to find this. So what are those intersection points going to be?
Would that be 1510, 1550, 4540, and 4550?
Yeah, 1510. That's that one. What about this? What did you say for this one?
4540?
Yeah, exactly right. Because that's the line x minus 5. This one right here is 45.
50.
Yeah. 4550. And this one right here, which I'm running out of room here, that one right there is 1520.
Yeah.
Does that make sense? Right. So my picture is wildly inaccurate. So it looks to me like y is going to travel. I mean, look at the y values. Y is going to travel between 10 and 50. Yes.
Yeah.
Right. So here's 10 and here's 50 up here. But there's going to be several chunks. I mean, first of all, these points in the middle should be inverted, obviously. Yeah. I mean, you understand my picture is just not accurate.
Yeah.
Okay. But because it's not drawn to scale. But so y is going to be between 10 and 50, right? Y is going to be between 10 and 50, but there are several special spots that we need to pay attention to. So the first spot is between 10 and where? Where's the first place that I need to change my thinking in terms of what x goes between?
That'd be x plus 5 or
No. What y is
no?
between numbers now?
Oh,
Like where's, I mean, so these numbers are ordered. It's 10, 20, 40, 50. And stuff changes at those various y values. So the first chunk is between 10 and
20.
20.
Yeah.
Yeah. And if I'm between 10 and 20, okay, which is, I'm so like y is going between this and this. Okay, again, the picture is more accurately drawn. Shoot, let me draw it over here. Okay, it's more accurately drawn like this. Um, see what I'm saying?
Yeah.
Okay, so this was the point 15, 10. What was this point? 15.
20.
This point was 45.
40.
What?
40.
And this one was 45, 50. Yeah?
Yeah.
So that kind of divvies up this region into like 3 chunks. Do you see it?
Yeah.
So the first chunk is when y is between 10 and 20. And what is x going between? So think about it. If y is between 10 and 20, x is going to be doing these little horizontal slices, yes? Okay. So x starts at 15 every time, and it goes to this lower line. Yeah?
Yeah.
And what lower line, okay, this lower line is the line y equal to x minus 5, right?
Yeah.
And this upper line is y equal to x plus 5. Okay. So x goes between 15 and the line, but the line you need to write in terms of y. So what is our x, write x in terms of y. So what's x equal to in terms of y?
Y plus 5.
Okay. So
Yeah.
that's the first chunk, right? That's chunk number 1. What's the second chunk?
Y goes from 20 to 40. And then x goes from y minus 5 to y plus 5.
Yes. And the third chunk?
Y goes 40 to 50.
Yeah. And X?
Y minus 5 to 45.
So that's a lot more complicated than than integrating in the other direction. Do you know what I'm saying?
Yeah.
So that means that you're going to have to split the integral up into 3 parts. Does that make sense?
Yeah.
And I am very confident that if you do it that way, you'll end up with the same answer. Clearly, the easiest order of integration in this case was letting X go between 15 and 45. And then Y, so if X is going between 15 and 45, you can see that Y is always consistently going between the same things, namely the lower line and the upper line. Yeah. But when you
Yeah.
the order of integration using Fubini's theorem, right, which you learned in Calc 3 apparently, right? You have to be careful about how to split the integral up. Make sense?
Yeah.
All right. Cool. Okay. What else?
So for the conditional probabilities, for the joint probability ones,
Yes.
that's a distribution, right?
Yes.
Like it's not a probability. It changes to a distribution because we still have another variable or another random variable, right?
So say that again?
So like even though we're like given a certain variable's value, it's still a distribution.
Yeah, but for every single individual value of the other variable, you get a slightly different distribution, but it's still
Okay.
distribution. Does that make sense?
Yeah.
It's almost like you're thinking in 3 dimensions. You're letting one variable kind of change, and then when that changes, you get a different distribution shape potentially. And the problem we just did, where we were letting, what was Y going between 10 and, was Y
50.
between 10 and 50 or something like
Yeah.
that, right? Depending on what value of Y we were at, we had a different distribution for X. Does that make sense? But
Yeah.
still a distribution, right? So you just get different distributions depending on what Y is. Now, if the in that's not that last example, that was a specific actually we were computing a specific probability in that problem, yeah?
Yeah.
But the density itself was just 1 over 1800, right? So no matter what Y was, in that case, we had the exact same distribution for X. That indicates that the 2 random variables are independent. But in theory, if there is dependency between them, a different value of Y could give a different distribution for X, but it's still a distribution. Okay?
Okay.
So these conditional distributions are still distributions nonetheless. Yeah.
Okay.
That kind of makes sense. It's a little confusing to wrap your mind around, but I think if you think 3-dimensionally, it's helpful. Like you're just imagining, like down in the XY plane, you're imagining like Y moving a little bit, and then you see what happens with X when for that fixed value of Y, and you'll just get slightly different distributions. And you can almost in your mind, imagine, like the distribution kind of changing depending on where X and Y are. Yeah. So, yeah. And in theory, if you integrate over both variables, you should still get 1, right? So yeah. Is that helpful?
Yeah.
Okay.
So I think the book briefly mentioned like the expected values of the marginal density functions.
Yeah.
Um, using that to find like the expected value of X and Y. But I was wondering if there's like a expected value of like the joint probability density function.
Oh, you mean like, well, yeah, you would use that if you had a specific function of both random variables, for instance. Okay, so let me do this again. So, suppose that XY has joint density f of XY. Okay, for, I don't know, XY belonging to some region. Okay, then, right, then what that means is like if I were to integrate over this region, whatever that looks like, f of XY, I'll just write dA, right? Because dA is like dx, dy, or dy, dx, depending on how I set up the region. Does that make sense? I don't want to specify whether it's dx, dy, or dy, dx. But this is going to be 1, okay? Because right, the xy is an ordered pair of random vector. Okay, we often refer to this as like a random vector. It has to be somewhere, and this joint density that we came up with is the thing that's telling us, that's the weight of the point x comma y. But if I had, like, I can compute things like the expected value of some kind of function of x and y. So I might have like xy minus y squared plus, 2x or something, right? And I could compute the expected value of things like that just using the density. So this would be the double integral over R, and you would just replace the big variables with the small ones. It would be xy minus little y squared plus 2 little x. And then the density is what weights all of those values, according to how, or how frequently, if you will, in quotation marks, they occur. Okay, so you would multiply that by the density dA, right? And so the density is what kind of weights all of the values of that random function of x and y properly. And if you were to integrate that, you would get the expected value of that thing. Is that kind of what you're asking about?
Sort of. I'm wondering if there's like similar to like we had an expected value of like just X. Is there a
Yeah.
similar one for the joint probability?
What do you mean? Like, oh, you mean if you were to, if you wanted just the expected value of X from the joint probability density?
Well, no, I know how to get that.
Uh-huh.
I don't, I've, so like, sort of, the expected value of X sort of seems like the most simple, like, expected value you can get for a distribution. Is there
Okay, yeah.
something similar for that, for the joint distributions?
Um, yes. The expected value of X times Y comes up a lot.
Okay.
The expected value of X times Y comes up in something called the covariance. I don't remember, did they mention covariance in chapter 6 or no?
No, not until chapter 7.
Yeah. So the expected value of X times Y is one thing that comes up quite a bit because that's kind of like a generalization of like the expected value of X squared where Y was equal to X. Okay. So like the covariance, I'll just write down the formula for covariance. The covariance is the expected value of, do you remember what the formula was for that?
No, I haven't gotten that far yet.
Oh, okay. Right. So what you do is you basically take X minus its mu, and now I have to be very specific about which mean I'm talking about, yeah? And you multiply that by Y minus its mean, okay? And this is an extension, so think about this for a minute, Matthew. This is basically an extension of the variance. Because if Y is equal to X, right, so note, right, and let's call this actually has a name. It's called the covariance of X and Y. Okay, so note the following. If you take the covariance of XX, what's the covariance of XX? Think about it.
It's
Well,
just the variance.
it's just the variance. Right, so this is going to just be X minus mu of sub X squared, which is the variance. Okay, so this is an extension of the variance, but let's actually compute this, okay, and come up with a formula. So if I were to multiply this out, you would end up with xy, right, minus mu sub x y minus mu sub y x plus mu sub x mu sub y, right?
Yeah.
And what happens if I take the expected value of these things? Let's think about it. The mu's are just, those are constants, right?
Yeah.
If I take the expected value of mu sub x y, isn't that just going to be, because I could factor out the mu sub x, the minus mu sub x, and that's just going to be minus mu sub x mu sub y, right?
Yeah.
And similarly, it's going to be minus mu sub y mu sub x. So it's going to be minus 2 mu sub x mu sub y. But then I'm also have a plus mu sub x mu sub y. So in the end, doesn't this just end up being the expected value of xy minus what? What's it going to be if I, what am I going to have to subtract off? It's going to be minus mu sub x mu sub y minus mu sub x mu sub y plus mu sub x mu sub y. So overall it's minus mu sub x mu sub y, right? And so you see that this thing kind of shows up in the formula for the covariance, okay? Shows up right there. And this is an extension of the formula for computing the variance. If y was equal to x, we would have exactly the formula for the variance. And you might say, why in the world would we be interested in such a thing? Well, it turns out that the covariance, it kind of measures, like think about this product right here. If the covariance was positive, wouldn't that mean, Matthew, that x and y, that this product was tending to be positive on average? Yes.
Yeah.
That's what this means. So if the covariance is positive, that would mean that this product was tending to be positive on average. And if that product is positive on average, that would mean that x and y as random variables were tending to be on the same side of their respective means. So like if x was above the mean, so was y, was above its mean. And if x was below its mean, then y was tending to be below its mean. So that product ended up being positive on average. Does that make sense? And if the covariance is negative, what does that tell you about how x and y were tending to behave relative to their means?
It would be on opposite sides.
Yeah, they're tending to be on opposite sides of the means. And so that's kind of measuring, are x and y influencing each other in some way? Like if x is high, is y high? And if x is low, is y also low? Or do they have the opposite? Or do they just not even pay attention to one another? The covariance is going to tend to be zero if x, in fact, it will be zero if x and y are independent. If x and y are independent, this expected value of x, y is just going to be the expected value of x times the expected value of y, and the covariance will be zero. But if the covariance is anything other than zero, that tells you that x and y are tending to be either on the same side of their mean or on opposite side of their mean, okay? And that is, there's a correlation between x and y. That's where the term correlation actually comes from. It's from staring at this covariance quantity, okay? So if the covariance is not zero, that means there is some kind of correlation between the random variables. They are not independent. They are dependent. And depending on the sign of the covariance, like if it's positive, that means that x and y are tending to be on the same side of their respective means. And if the covariance is negative, that means that x and y are tending to be on the opposite sides of their respective means. Okay? So there's some kind of influence one over the other. And so this is where the notion of correlation comes from staring at the covariance. This is it. So that's why I say that the expected value of x, y is a very important thing to look at. And you can see that it's a nice extension of the sorts of things that we were interested in when we had just one variable, right? Namely, like the expected value of x squared, for instance. Okay? I don't know, hopefully that's kind of helpful, but yeah. Covariance is a big deal, no question. By the way, I mean, I riff on this quite a bit, but there tends to be a lot of massive misunderstanding from media people. They use the term correlation as if like there's any influence at all from one variable over another. But actually, the covariance is only measuring a certain kind of relationship, because we're looking at x and y compared to their means. We're not looking at like maybe e to the x and e to the y would, you know, behave differently. So correlation is measuring linear relationships between x and y, okay? Like you're basically just comparing it to their means, and that's it. So the term correlation just gets abused in popular media because they act as if that correlation just means that there's some kind of relationship. When in fact, all correlation means is that there is a specific kind of relationship, namely linear, between two variables in question. Does that make sense? It's not measuring other kinds of relationships. It's only measuring linear relationships. Okay? So they say there's no correlation. I just want to say, you fool. There might be other kinds of relationships going on, you know? Just because there's no correlation does not mean that there's not a relationship. So that gets muddled quite a bit in popular media for sure. What other questions do you have?
So I was having a bit of trouble with problem 45. I'm not sure if I was understanding it correctly.
Okay. So every one of these motors comes with its own density, yeah?
Yeah.
So what would the density for all, okay, so like, you have three, or you have five things. So xi is equal to, right? So if each motor independently functions for a random amount of time with that density, okay? So xi is equal to the amount of time a motor I functions, right? And apparently, the density, so each xi has density f of x equal to x e to the minus x. Okay, and is that for x bigger than 0?
Yes.
Okay. So what is the density for the random vector x1 through x5 going to be? Since they're independent, right? These guys are independent, right?
Yeah.
So what is the density for all 5 going to be?
It would just be the densities multiplied together, right?
Yeah. So the joint density for the random vector x1 through x5 is, let's use g of x. Well, actually, g of x, x1 x2, x5, which is equal to what? So what is the density going to be? It's
It
a
would be
variable function.
x1 times x2
Yeah.
times x3 to 5. And then e to the negative x1 plus x2 plus x3.
Okay. So that's what the joint density is. Yeah, it's like a 5. We can't really visualize this, obviously, because it's all happening in 5-dimensional space, right? But that's what the density is going to be. I promise. And by the way, so what's the requirement here? Well, x1 through x5 all have to be bigger than 0. Yeah. So if you integrate on the 5-dimensional, uh, I don't even know what to call it, where x1 is bigger than 0, x2. So whatever that hyper sector is, if you integrate over that whole thing, you'll get 1, okay, for this joint density. But the problem here is asking us, what does it say? So as long as 3 of its 5 motors are functioning, or as long as at least 3 of its 5 motors are functioning. Okay, and they want to compute with density compute the density function of the length of time that the machine functions. Okay, so how can we take this information and create a density that tells us the length of time that the machine functions? What do you think?
So like I kind of assumed we would integrate like 0 to t, I guess, the density.
Okay. 0 to t. So what are you thinking about when you do that?
Like sort of like the probability that it will function a certain amount of time.
Yeah. Um, so at least 3 have to be functioning at any given time. Right. But I guess how are you thinking about, like, so integrating from 0 to t, like we have 5 variables we're dealing with here.
Yeah.
So what are you thinking about doing?
So I didn't write it in terms of 5 variables. So I assumed that since they were like independent and sort of identical, that I would
Oh,
just
so
do
you
it
just,
for,
oh, I see. So you integrated, I see, I see. Yeah. So if you integrate one of these things, I see what you're saying. So you're saying that the probability that xi functions so the probability that xi is like less than or equal to t,
yeah,
right? Is what?
be the integral from 0 to t x e to the negative x
Yeah.
dx.
Okay. So then did you integrate by parts, I'm assuming?
Yeah, I came out to 1 minus e to the negative t times the quantity t plus 1.
What's e to the negative t so is it 1 minus e to the t in parentheses times t plus 1, or just one, right? Because I mean, I guess I could go through it. If u is x, dv is e to the minus x dx, right? du is dx, and v is negative e to the negative x,
Yeah,
right? So this is going to be equal to a negative x e to the negative x evaluated between 0 and t, plus the integral of e to the negative x from 0 to t dx. Yeah.
yeah,
So the 0 dies, right? So this is going to be minus t e to the minus t. Okay, and then it's going to be plus, let's see here, it's going to be minus e to the minus x evaluated between 0 and t, right?
yeah,
So then I get minus e to the minus t plus 1, right? So 1 minus t e to the minus t minus e to the minus t. Okay, so I think I see where you got this. So it's equals 1 minus e to the minus t times the quantity t plus 1. Got it. Okay. So how could we use that? So every single one of these variables has their own, so this is basically the CDF, right? It's the CDF of each one of these variables. Yeah.
yeah.
Okay. So how could we use that? So tell me what you did with that, or what you were thinking about doing with that.
So since we needed, I guess, 3 out of the 5 to be successful, um, I set it up as like a binomial.
Okay.
Um, I'm not sure if I'm really allowed to do that, but
Okay. Right. So then what? How are you going to use the binomial? I mean, that's the approach I would have taken, yes. But how are you going to use it?
um, so I think if what we calculated was a CDF, that's the probability that it like lasts up to t, but if we want it to last greater than t, we would need to do 1 minus that, right?
Yes.
And then we would,
So the probability the probability that any of the xi's happens to be greater than t is going to be e to the negative t times t plus 1. Right?
Yeah.
And that's for t greater than 0, basically. Okay.
And then I kind of treated that as the success in the binomial.
Okay.
So I had like the sum from 3 to 5, 5 choose k, times that to the k, times 1 minus that to the 5 minus k.
Well, okay, so like if y is equal to the time machine lasts, yeah?
Yeah.
Then what is the probability that y is greater than t? What does that mean? Let's kind of write out what that means.
It would mean at least 3 of the 5 machines.
Yeah, that's equal to the probability that greater than or equal to 3 of x1 through x5 are greater than t. Yeah?
Yeah.
Okay. So we could kind of split that up into either exactly 3 or exactly 4 or exactly 5 of those last at least that long, right? Does that make sense?
Okay.
Okay, so what would that be?
5 choose 3 times the quantity e to the negative t times t plus 1 to the third.
Yeah. Okay, that's if exactly 3 lasts longer than t. Yeah?
And then, oh, we need to multiply it by 1 minus that to the second,
Yeah, because
right?
the other ones have to be smaller. That's exactly right.
Okay.
Right? So then it would be, oh man, that's annoying, right? So then it would be 1 minus e to the negative t times t plus 1 squared. Yeah?
Yeah.
Yeah, so you're kind of treating this as like the probability of success or something, right?
Yes.
Right. And then it's going to be plus what?
5 choose 4 times the success to the fourth. And
Yeah,
then
p to the fourth, q to the
first.
third, q to the first. Yeah. Where what's p? P is, or hang on. This is p up here, right?
Yeah.
Okay. And what's the last one?
5 choose 5 times p to the fifth.
Yeah. Yeah, I think that's it. That's crazy. What should be true about that, I guess? I mean, is there something, I mean, what could we do with this to, but that's actually, I mean, hang on a second. Look at that thing. That's the probability that y is greater than t, right?
Yes.
What would the CDF be for this thing? Did they ask for the density or the CD? So the CD, they
Um,
want,
it says the density.
right, so capital F of t for y, that's going to be 1 minus this probability, right?
Okay.
Which is slightly annoying. In fact, it might have been actually easier since we had 3 terms anyways. It might have been easier to just do the probability that it might have been it might have been easier to actually just do the probability that y is less than t. You know what I'm saying? What would that mean?
Um, only 0, 1, or 2 function.
Yeah.
Like, yeah.
So that might be easier to do. So 0, 1, or 2 function. If 0 function, that would be like q to the 5th, right?
Yeah.
Where q is defined from that previous slide, yes?
Yeah.
Plus what?
5 choose 1, p times q to the 4th.
Plus,
5 choose 2, p squared times q to the 3rd.
right? And those p's and q's are fairly horrible, right? So what we're saying here is that all 5 have failed. Yeah. Or
Yeah.
exactly 4 have failed at this point. Or exactly 3 have failed at this point. But that's the CDF, Matthew. So how would I get the density?
Differentiate.
Yeah. Yes. So Fy of t is going to be the derivative of this thing. Which seems like it might be awful, but maybe there's, I mean, I could factor out q cubed, for instance, right?
Yeah.
So I don't know. I mean, one thing you notice is that if you factor out q cubed, what's left behind? That's 1 plus 5p plus what? Okay, it's plus 10 p squared, right?
Wait. What happened to the other q's?
Huh?
What happened to the q squared and
Oh,
q?
sorry. Yeah,
Uh,
yeah.
okay.
Thanks. So what is it? Q squared plus 5p
2p. Yeah.
plus p squared. Okay. Okay. That's interesting. So I think, let me see here. I'm sort of obsessed with this problem at this point. So what if we went in, let me see. Let's see. So can you read stuff off to me? So what is it that, okay, so what was the, um, what was Q again? I forgot.
Q was 1 minus e to the negative t times the quantity t plus 1.
Oh, right. And I want that to be cubed here, yes?
Yes.
And then I want to multiply this by
Um,
q squared. Here's this. Here's q right here, right? Q squared times, oops,
um,
plus, right?
yeah.
5q
P. Um,
5q times p. What's p?
just take off the 1 and the minus sign for cube. And then,
This.
yeah.
Okay. Plus
10 p squared.
hopefully I have the right amount of parentheses here. I think I do, though. Man, that simplifies quite a bit. You serious? Look at that thing right there. Let's make sure that this did the right thing. So q squared plus 5qp plus 10 p squared. Yes. Amazing. So the other thing that I would be interested in knowing, so you see this right here. So this is what it is apparently. What should this thing integrate to if I integrate from 0 to infinity?
1.
Yeah. So watch this. I can go plain text, grab this thing, copied. Are you serious? Let me go over here into this other one. I don't want all that other junk, right? So I want to integrate this from where to where?
0 to infinity.
Yeah. That's going to be horrible to integrate by hand. We're gonna have to do all kinds of like integration by parts. Yes. It integrates to 1. That's sort of amazing. Okay. So that has to be the answer, Matthew.
Okay.
That was thanks for asking that. That was a fun little exercise. Do they have an answer for that one or no?
I don't believe so.
Okay. Well, but we're pretty confident that that's the answer, right?
I think so. Yeah.
Yeah. Cool.
Okay.
Yeah.
Thank you.
Yeah. Thanks for coming in and asking such good questions. Appreciate it. All right. Have a nice weekend.
You too.
All right. See ya.